Welcome, welcome, welcome. In this video, we're going to discuss the shifting trick, and it's going to build us up to a formula that will give us the maximum number of coins that we can deal with when we don't know if our counterfeit coin is a little bit too heavy or a little bit too light. So the shifting trick is where we're going to start, and this trick is going to give us a non-adaptive solution to some, maybe not all of them, but some of them, these coin weighing problems that we're dealing with. So which ones can we get some help with the shifting trick? Well, when the number of coins is a multiple of 3. So if I give you a coin weighing problem with 3 or 6 or 9 or 12, the shifting trick might be really valuable. And the next sentence says something else that's also helpful. We can add 3 coins to some existing non-adaptive solutions. So if you already had a solution that gives you, a successful way of figuring out the counterfeit with 5 coins, you could add 3 and get 8. If you already had 8, then you can add 3 and get 11 in that sort of fashion. Okay, so how does it work? So we're going to devise a way of successfully placing 3 coins on the scale. So first, take any way that the scale can respond other than all L's or all R's or all B's. Those methods won't lend itself to this step working out. So we have to avoid those ones. So pick something different. And then we're going to shift according to this diagram. If you have an L, it becomes a B becomes an R becomes an L. And we'll explain what we mean by that below. So for example, if we have 3 weighings, and that's what we're trying to deal with, we have to pick something other than all L's or all R's or all B's. Let's say we pick this response here. And remember, every coin is paired up with these 2 responses when the coin is on the scale at least once. So we could use either one of these. Let's just pick the LLR to focus on. So what we do with the LLR, as we notice in the diagram, the L shifts to a B and the B shifts to an R. And then we get 3 possible ways of putting coins on the scale. Out of those 3 ways, we're going to call those things shifting sets. So LLR goes in the first shifting set. It shifts to BBL is there. And BBL shifts to RBB, and RBB is here. So we always have to pair them up. So the responses that are paired are also here too. In a similar way, you can build all the other shifting sets. So that's what you do in step 1. Now, if you didn't have to deal with that many coins, maybe you don't need to note all of the shifting sets, but we did here so that we'll have them handy when we continue through our video. Okay, so what do we do after we've discovered our shifting sets? We use them to place coins on the scale. So, for example, if we use the shifting set that we were focusing on above, we'll place coin 1 with LLR. So left, left, right. And coin 2 will get the second part of our shifting set, balance, balance, left. So coin 2 is balance, balance, left. And then coin 3 is right, right, balance. So right, right, balance. One way to visualize this is once we start by placing coin 1, and place coin 1 there, there, and there, you can visualize by that diagram that we had above, you can just shift to the 2 and shift to the 3, and that builds what you do with those 3 coins on the first weighing. You can do the same thing with the second weighing, and wherever coin 1 is, wherever you're starting, you just shift according to that counterclockwise loop. Mathematicians seem to like counterclockwise, so I use counterclockwise for this. So we can keep adding more coins if we like. So if we wanted to add more coins from another shifting set, we could add coins 4, 5, and 6 in a similar fashion. Just pick any way of the scale responding that hasn't been used so far. So in this example, maybe we picked RLL, and we placed coin 4 according to that plan on the right, on the left, and then on the left again, and then we shifted it according to our diagram in that counterclockwise fashion. So 4 gets shifted to 5, 5 gets shifted to 6. And this successfully places 3 more coins on our weighing so that we could now have a successful solution with 6 coins. So one extension that you can do, that, as we discussed before, is you don't have to just restrict to multiples of 3. You could add 3 coins to an existing solution. So the trouble is you need to get that existing solution to begin with, but then once you've got it, then you can continually add 3 coins at a time to it. You have to make sure that no part of the shifting set is already being used. So remember, we can't repeat any scale responses ever, because then there would be a conflict between 2 coins that would have the same response, and you wouldn't know which coin is the counterfeit. Our job is to figure out that counterfeit. So in this example, we're going to play around with the extension. So we have 8 coins, and we've conveniently numbered them 1 to 8. A successful non-adaptive solution is given below for 5 of the 8 coins. So we're going to use the shifting trick to extend this solution to have 8 coins. So we can pick any response that is not already a part of a shifting set. So below, what we've done is written out the shifting sets. Let's try to identify which shifting sets we can use. So RRL is already used. So RRL is in the first shifting set. That means that we cannot use that shifting set, because we would have a conflict with coin 2. Let's look at the next coin, coin 3, LRR. LRR appears right there, so we cannot use shifting set 2. Okay, so then the next one, RLR, appears right here, RLR, so we cannot use shifting set 3. And luckily enough, there's a 4th shifting set that doesn't have any conflicts with our coins so far, so we can use that one. So let's start placing coins on the scale. So coin number 6, we will use balance left, right. So coin 6, balance, and then on the left, and then on the right-hand side. And then we will shift this coin according to our diagram for the shifting trick. So in each one of these cases, we shift in this counterclockwise fashion. So for coin 7 and 8, they get placed accordingly. And now we've successfully placed coin 6, 7, and 8 on our scale according to that last shifting set. So let's fill in the rest of the chart. So that completes our solution of adding 3 coins to this existing 5 coin solution. Now we can tell any one of the 8 coins that might possibly be the counterfeit, either too heavy or too light. Okay, so next we're going to try to explain what the maximum number of coins we can deal with in general is, and we'll start with what about with 3 weighings. So we're going to try to solve the problem for 13 coins. So once again, what is the problem? We have 13 coins, all identical. One is slightly heavier or slightly lighter than the others, and our job is to find the counterfeit in 3 weighings on a pan balance. We're going to make use of our shifting trick here. So we've found ourselves a nice little table here with all the shifting sets laid out nicely. So from here, all we have to do is label our coins according to the shifting sets. So we'll just go in order: coin 1, coin 2, and coin 3. So coin 1 gets placed on the left, left, right. So coin 1, left, left, right. And then coins 2 and 3 shift in the counterclockwise direction. So 2 is off, and 3, 2, and 3, and 2, and 3. So next up, we have coin 4, 5, and 6. So coin 4 will get put in the right, left, left position. So coin 4, right, and then left, and then left. And then coin 4 shifts to 5 and 6 in the counterclockwise direction. Coin 4 shifts to 5 and 6. Okay, that's the second shifting set. Now for this third shifting set, we'll do coin 7, 8, and 9. We'll start with coin 7. It goes left, right, left. So left, right, and left. And now coin 7 shifts to 8 and 9 in each of the cases. 8 and 9 and 8 and 9. And the final shifting set is similar. So that makes use of our shifting trick as much as we can. Now there's 2 more responses that we could possibly use. We're asked to do 13 coins, and we can't use the left, 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 or right, right, right response at this point, because that would throw 5 coins on one side of the scale where there's only 4 on the other. So we can't use this one at this point in our solution. But we can make use of the balance, balance, balance option and place coin 13 there. So coin 13 gets left off of the scale each time, and we have a successful solution with 13 coins. So next, we're going to try to convince ourselves that this is the maximum number of coins that we can deal with. So we can't solve this problem with 14 coins. 14 would be one too many. So why not? Let's try to think about this. Why can't we use all possible responses that are given? If you used every single one of these responses, no matter how you decided to place coins on the scale, like there is a bit of a choice here, because one could be placed according to this one, the left, left, right, which is what we did, left, left, right, but you could also use the other possibility, right, right, left, and we didn't make that arrangement. So there might be different ways of mixing things up, but if you used every single one of these, then what would happen is there would still be 5 coins off of the scale, right? Because all of the options with B's are used. That would mean that there is 9 coins left. There would be 9 coins on the scale. And that won't work because we have to have an even amount of coins on the scale, because we have to have the same on the left and the right. So let's write down our solution. So first, assume that you can solve the problem with 14 coins. Okay, then all the responses are used. But then it must be the case that 5 coins are off of the scale for each way. Let's write that down. And if 5 coins are off of the scale, and there is 14 coins in total, it means that 9 coins are on the scale. Let's write that down. But here's a contradiction, because we always have to have an even number of coins on the scale. So my favorite symbol for a contradiction is a lightning bolt. So the math gods come and strike us down here. We've said something incorrect, that we've assumed that we can solve the problem, but we've thrown 9 coins on the scale. And the problem is that we always have to have an even amount on the scale, the same amount on either side of the pans. So this means that what we assumed must be wrong. We assumed that the problem can be solved with 14 coins, So therefore, the problem cannot be solved with 14 coins. Okay, so this leads us into a general theorem that holds for coin weighing problems. For our course, we're going to call this the coin weighing theorem, part 2. So let's remind ourselves of the difference between part 1 and part 2. So in part 2, our counterfeit is either slightly heavier or slightly lighter. In part 1, we knew that the counterfeit was just slightly heavier. So what we do is take the number from part 1, divide it by 2, and take the floor of that result. That will give us the maximum number of coins that we can deal with given a certain number of weighings. So there's a handy little chart below that we should fill in some numbers. If we have one weighing, we actually can't do anything. We can't identify any more than just one coin. So even if you had 2 coins and one weighing, the scale would tip and you wouldn't know which one was counterfeit because it could be too heavy or too light. But once we get 2 weighings in the mix, then we can start dealing with this problem. So we take 3 to the power 2 and divide it by 2. So we get 9 divided by 2, which is 4.5. And if we round that down, we would get 4. If we wanted to do one more weighing, this is what we just did above. We would take 3 to the power of 3 this time for 3 weighings. Divide that by 2. So 27 divided by 2 would give us 13.5. And then we round that down to give us 13. Let's do one more. So 4 would give us 3 to the power 4 divided by 2, rounded down. So we've got 81 divided by 2 is 40.5. Rounding gives us the 40. So this pattern goes on and on and on as the theorem explains, giving us the number of weighings and the maximum number of coins that we could deal with that number of weighings. Okay, thank you so much for listening, and we'll see you on the next one.